Hey, what's up, everybody? I wanted to talk to you today about gametes or sex cells and kind of debunk some of the myths that people have about these cells, and just talk about the process of how they're developed and how they're totally different in males from females. So let's go ahead and get started with this. I'll go ahead and pull up um, some notes that I want to share with everybody. Let's get to this slide right here. And I want to talk about the process of making sex cells known as gametogenesis. Now, please understand that sex cells are gametes. Okay. Basically, if I broke your body down into two groups of cells, they would either be somatic cells or gametes, sex cells. Somatic cells are all the other cells that make your body, everything from your skin cells to your muscle cells to your nerve cells. Those are somatic cells. They make your body. They undergo mitosis, they divide, and you get more cells that are completely identical. And guess what? Um, they go on to become specialized cells, or they go on to become father cells or stem cells and divide and become more. And that's what you do. Every time you undergo mitosis of somatic cells, the goal is to make more somatic cells. But that's not the goal of gametes. Gametes undergo mitosis for the simple fact that they need to create more numbers. But then after going through mitosis, sex cells or gametes, they undergo meiosis, which its job is simply to diversify the genetic material that they have and then split that genetic material into half, i.e. 23 pairs of chromosomes. And the reason why is because the goal of a gamete or a sex cell is not to simply make more sex cells. The ultimate goal is to pair its half of its chromosomes with the half of another gamete, an opposite gamete. So if we're talking about a male gamete, then its ultimate goal is to share its half of the gametes with half of the gametes of a female sex cell. In other words, when you show up with a gamete, it's going to have 23 chromosome pairs. But in order to make a human being, you need 46. So you pair a sperm cell with an egg cell, and that 23 plus 23 equals to 46. So when you look at this slide, you see that sex cells are termed gametes. You have female gametes and you have male gametes. Unlike somatic cells, you got all kinds of somatic cells, everything from hepatocytes, which are located in your liver, all the way to simple squamous epithelial cells that you find in your capillaries, to your cardiac cells, which are in your heart, all the way to oligodendrocytes that are floating around in your brain, that are attached in your brain. So you've got all these different somatic cells in your body. But gametes, on the other hand, you only got two kinds. That's it. You got sperm cells, and you got oocytes, which are egg cells in the female. I want you to pay close attention to something in this slide. You'll see where it says secondary oocytes. Don't forget that. Okay, we're going to play with that a little later on in this video, but I need to speed up so I can get further along. Both of these gametes are going to undergo mitosis and meiosis. Remember, mitosis is the process of somatic cell division. So before that gamete becomes mature, it's going to undergo mitosis. All you're doing is creating more cells for the sake of creating more numbers. That's all. You are not creating the end product. This is to get more of a product so that you can ultimately have more of an end product. But it's not complete, because when it undergoes mitosis, it still has 46 pairs of chromosomes, which you can't take a cell with 46 chromosomes and put it with another cell with 46 chromosomes and come up with 92 chromosomes in a person. No, and you're not going to make two people out of that 92. No, you're not going to do it. It's got to be 23 and 23 put together, slapped together to make a person. So at this time, we've got mitosis down pat. We've made more cells. That's great, but that's not the end product. We have to undergo meiosis, which is known as reduction division. In this case, what we do is a specialized cell division where we take these cells, they start acting more like gametes. We produce haploid daughter cells. In other words, beforehand, we were producing diploid daughter cells, where they have the same number of chromosomes as the father cell, the original cell, the original stem cell. But when we undergo meiosis, we create two daughter cells that happen to be haploid. In other words, they have half the genetic material. In other words, 23 pairs of chromosomes, which is perfect for what we want in a gamete. So, when we look at meiosis, really meiosis is actually two cycles. When you look at mitosis, remember, mitosis is basically just four stages. Mitosis is prophase, metaphase, anaphase, and telophase. Just four phases that the cell undergoes, and in a matter of a series of minutes, you've got mitosis done, and you've got two identical, completely identical cells, where at the beginning you only had one. What's interesting with meiosis is, in meiosis, what winds up happening is you wind up with two. And when you fuse a male gamete with a female gamete, it's going to create the correct cell with the correct number of chromosomes, which is 46, 23 from each parent. And so you therefore have the genetic diversity necessary to produce life. So when you look at this slide, you see meiosis 1, you see meiosis 2. I'm going to be honest with you. It depends on your teacher as to how much depth or information they want you to know about meiosis 1 and meiosis 2. Meiosis 1 and meiosis 2 actually have the same phases as mitosis, except the primary function of the phases in meiosis 1 and meiosis 2 is not simply to make an evenly divided cell. Its goal is not to say, hey, look, I got two completely identical cells. That's not the goal of meiosis 1 and meiosis 2 and the phases within it. The phases within it is really to create enough genetic diversity so that you get a healthy mix of the genetic material that's there, and that you wind up with enough cells at the end with half of that genetic material so that you can hopefully recreate, so that you can reproduce. So when you look at meiosis 1, you'll see you've got this cell, and he's already been duplicating things, and then he's going to undergo a split. Now, when he undergoes the split, he's already, changed up the game here. He's taken the genetic material here. He's diversified it here along this line, along the equator there. He divides up that genetic material nicely, and then the cell splits. Well, guess what? Both of those cells are going to undergo meiosis 2. We're going to take this diversified genetic material, bring it to the middle at this equator, and then we're going to split it again, which is going to wind up giving us 23 chromosomes per cell, because here we just doubled up everything and these guys divided off. But what's going to wind up happening at the end is we're going to wind up with 23 chromosomes per cell. So we start off with one gamete, but in the end we end with 4. Whereas in mitosis, we start off with 1 and we end up with 2. So the primary thing that I would personally want my students to remember out of all of this is that meiosis only happens to sex cells, and that it's all about getting a diversification of genetic material, and that at the end of the game, we want to see 23 chromosomes at our end product versus 46. And we start off with 1 cell here at the beginning of all of this, but we end up with 4. So when you look at gametogenesis overview, I like this chart because it really keeps things simple. The stem cell that you're talking about when you're talking about men is a spermatogonium. The stem cell when you're talking about women is a oogonium. During mitosis or mitotic division, you wind up creating one primary spermatocyte and a stem cell. In oogenesis in the female, you create one primary oocyte and one stem cell. Now remember, this happens in any mitotic division of any cell. If you have mitotic division of any cell in your body, you will ultimately want cells, and then one of those daughter cells has to decide if they're going to carry on the family business and if the other daughter cell is going to become specialized and leave home. The daughter cell that decides to carry on the family business is going to become a stem cell as well, and it's going to undergo mitosis. Whereas the other daughter cell is going to leave home and strike out on its own and become a specialized cell. It's going to upgrade. This is happening in both cases. Meiosis 1 is when we see the real difference. In Meiosis 1, that primary spermatocyte then upgrades into a secondary spermatocyte, into secondary spermatocytes. Okay, because remember previously in Meiosis 1, we saw where we had that split. See over there on the left where everything's in blue under the blue bar? We started with this dude, and now this primary spermatocyte becomes two secondary spermatocytes. Whereas in Meiosis 1 for the female, something's different. We wind up with one secondary oocyte. And that's because we did not make an even split, like the even split that happens here in the male. No, there is no even split in the female. Instead of getting an even split, the secondary oocyte winds up taking all of the cytoplasm and all of the organelles to it, leaving this polar body thing with a nucleus and random fragments of cytoplasm and cell membrane. So that polar body is useless. It's going to have to get reabsorbed and broken down and done away with. Then we move into the process of meiosis 2, and then things get even more weird, because in meiosis 2, the secondary spermatocytes turn into 4 spermatids, undifferentiated male gametes. In other words, spermatids do not look like, they have not physically matured. Okay, so they have not physically matured. They we got these cells and they got the genetic material in them, but they are still undifferentiated. They have not become fully fledged, physically mature and physically functional sperm cells. They don't look like sperm cells yet. They're still missing some parts. They're not quite there yet. Meanwhile, in the female, we can wind up with an ovum and a polar body after fertilization. As you can see, this is crazy, because an ovum is a fertilized egg. All right. An ovum is an oocyte that is fully mature, but you cannot have a fully mature oocyte unless you combine the genetic material from a sperm cell to a secondary oocyte. So what is this telling me? What this is telling me is that every time a woman ovulates, she is ejecting a secondary oocyte, and that secondary oocyte is never going to become a final product until it comes into contact with the sperm cell. So when you go back here, basically what's happening is I get to about somewhere around here, you get to prophase. I want to enlarge this actually. Let me go back. Let's enlarge this because I want you to see something here. Okay. So we're in meiosis 2, and I want you to remember this phase right here. I want you to remember prophase 2 and metaphase 2, because I'm going to skip forward. I'm going to show you something about prophase 2 and metaphase 2. Let me skip forward and show you what I'm talking about right here. Now, you remember I said that in the male, we go through this, and we go through mitosis in the male. You then wind up having one of the cells continue to go through spermatogenesis, and the other cell just becomes a sperm cell, a sperm stem cell. All right. Well, and then that cell that continues on through spermatogenesis goes on through meiosis 1, goes on through meiosis 2. It winds up being a spermatid, and then it finishes out spermatogenesis through a phase called spermiogenesis, where it becomes physically mature and it actually looks like a sperm cell. And whereas we started this entire party with one stem cell, we're going to end up with 4 sperm cells. Well, for the female, things are different. Oogenesis, we wind up having mitosis take place, and then we take one of those cells, and then that cell undergoes oogenesis, and that cell goes through meiosis 1, and instead of getting 2 complete primary oocytes, we wind up with a primary oocyte and a polar body, and that polar body is just made up of that second guy who didn't make it. and then that primary oocyte becomes a secondary oocyte, and then it stops. It does not make it all the way through meiosis 2. It pauses halfway through meiosis 2, and meiosis 2 is not completed unless fertilization takes place. And you can see here on the left side of this, this is where things get really complex. This is absolutely fascinating. Oogenesis starts in the female before birth. Yes, you heard me correctly. A woman starts making her egg cells before she's even born. Men, we don't do that. Men do not make any sperm cells while we're still in the womb of our mothers. Men don't start making sperm cells until puberty. All right. But women, you start making gametes all the way before you're even born. So if you look here, you can see the oogonium, which are the egg stem cells, and they all have 46 chromosomes in them because they're stem cells. And they undergo mitosis, and you wind up having these primary oocytes. Okay. And the primary oocytes, they are there, and the primary oocytes start the process of meiosis, but they're arrested in prophase 1. So guess what? These primary oocytes start meiosis, and they stop right there. So the entire time that this little girl is growing up as a child, the ovaries are inactive. It's got all the primordial follicles, which are housing the oocyte, and some atresia of the primordial follicles occurs. So basically, several of these primordial follicles are going to undergo cell death, and they're going to be reabsorbed into the body. Meanwhile, this girl finally hits puberty. So let's say this girl hits puberty at the age of 12 or 13. Okay. That primary oocyte winds up, you see here, up to about 20 primordial follicles mature into primary follicles every month. Some primary follicles mature into secondary follicles. Primary follicles that do that do not mature, undergo atresia, so they never make it. So here's one of these magical primary oocytes. Okay. It's been in cryostasis. This primary oocyte is the same primary oocyte that we were looking at here that you created before you were born. You created this primary oocyte when you were like 7 months in the womb. And this joker has been around since you were 7 months in the womb. And now this little girl is 13 years old. She goes into puberty. And now this thing is going to continue through development through her ovarian cycle. And this thing goes from meiosis 1 into meiosis 2. And as soon as it gets to meiosis 2, it pauses again, because we've now undergone meiosis 1, which creates this split. Now we got these guys 23 and 23. And this little polar body right here, 23 chromosomes surrounded by a little bit of goo, is not going to get anybody pregnant. So it degenerates and we lose it. We throw it away. But this one over here, this is usable. This is now a secondary oocyte. He's a haploid now. He's got half of the genetic material. And we're going to take this secondary oocyte. It's going to get ovulated on day 14, and it's floating around. Why is it floating around? It's in a uterine tube, a fallopian tube, floating around waiting for a sperm cell. If it encounters a sperm cell, then it will complete meiosis 2. It will upgrade into a mature ovum, and we will see someone get pregnant. But if it never encounters a sperm cell, then it will remain frozen in halfway through meiosis 2, and it will go on to be expelled or reabsorbed or just die. That cell won't be used for anything unless it can encounter a sperm cell. So unless it encounters a sperm cell, it just sits there with its 23 chromosome pairs, and it does nothing else. All right. That's talking about oogenesis in a nutshell. How does oogenesis link up with follicular development? Well, the entire time that we've got this egg cell developing, it is ultimately placed into a follicle for safekeeping. Think of the follicle as an incubator, and the follicle takes care of the cell. Notice that nothing's happening in the follicle until that girl hits puberty. And then we can track the growth of the follicle and the development of the follicle until day 14, ovulation. We are working off of the assumption that this young lady has an average of 28 days in their ovarian cycle, and that on day 14, they will ovulate, which is seen here, where the follicle ejects the secondary oocyte, and that secondary oocyte is still frozen halfway through meiosis 2. If that cell encounters a sperm cell, then a corpus luteum will be formed out of this previous follicle. And if this person gets pregnant, then the corpus luteum will stay the entire 9 months that that person is pregnant. However, if that person does not get pregnant, the corpus luteum will die. It then turns into a corpus albicans, and we start this entire process all over again. Instead of going up here, we start here, where the next primordial follicle steps up and becomes a primary follicle and moves on. One last thing before we wrap this particular presentation up is we need to go take a look at spermatogenesis, just to make sure that you can keep that separated from oogenesis. Spermatogenesis, you're going to find out, is extremely simple compared to oogenesis. In spermatogenesis, you'll see that spermatogenesis starts out here in the outer wall. This is a seminiferous tubule. Imagine a water hose all coiled up in one big knot. That's the seminiferous tubules. And if we take that water hose and we split it open and we look straight down in it, this is what we will see. Sperm cells start their growth process out here in the outer walls here, these walls lining the seminiferous tubules. And the spermatogonia, which are the stem cells, are out here on the outermost part of the wall. And they undergo mitosis, which then leads us to having primary spermatocytes. And these cells continue to get moved through this aqueous-like wall, and they go from primary spermatocytes into meiosis 1, which creates our secondary spermatocytes, which go through meiosis 2 to produce these spermatids. Now, when we produce these spermatids, this is when we have our 4 haploids. All right. This is the first time that we see cells in spermatogenesis really start looking like the haploids that we require. Now, usually, when you look at oogenesis, you remember that the oocytes looked more like these haploids here. But we have an entire another phase that we've got to go through here, because the egg cell in the female does not have to travel very far. It gets ovulated from the ovaries. It floats up, thanks to the fimbriae guiding them. They float up into the uterine tube, and then they sit there in the uterine tube and wait for sperm to arrive. Versus here in spermatogenesis, we've got to package and prepare the sperm cells to be able to travel. They're going to have to travel all the way from the vaginal canal all the way up to the uterine tube. So we have to physically change the spermatids into these sperm cells, these spermatocytes, so that they'll be travel ready. So these same cells, what they're undergoing is something called spermiogenesis. It's when they go from haploids that look like the egg cells in a female to the sperm cells that we commonly know in the male. These cells, and you can see spermiogenesis off to this box to the right. This is a spermatid. This is a haploid cell. It's just not going to be able to travel and make the trip. So what it winds up doing is it winds up undergoing a physical transformation. Here we can see the flagellum immediately being created, and we can see the developing acrosomal cap, which is being pushed and moved out towards the outer portion of this thing. We have to have the acrosomal cap take place and be produced on the head of the sperm cell, because the acrosomal cap is full of a specialized enzyme that's going to break through the zona pellucida wall of the egg cell. Kind of imagine the Death Star. You know, the Death Star in Star Wars has a force field around it. No shots can get through it to destroy it. but that acrosomal cap is an enzyme that could actually break through the force field, allowing the X-wing fighters sperm cells to actually make it in and actually cause the union between the sperm cell and the oocytes, therefore leading the secondary oocyte the complete meiosis two, and then become a fully mature egg cell known as an ovum. And by that time, sperm cell and the egg cell are uniting their 23 pairs of chromosomes to make 46, therefore upgrading this puppy to a zygote, and ultimately 9 months later, bringing forth a little person. All right. So that's all we've got for this particular talk. Hopefully we'll return shortly with another talk. We're looking at talking about comparing the ovarian cycle with the uterine cycle. We'll talk about that a little bit and the hormones that are involved with that. So stay tuned. If you got any more questions about what we talked about today, just post them on the site, and we look forward to seeing you soon. Peace.